The universe speaks in languages we are only beginning to understand. Gravitational waves, ripples in the fabric of space-time itself, carry messages across billions of light-years. Light, in all its wavelengths, tells stories of creation and destruction. In August 2025, these two messengers arrived at Earth simultaneously, bearing witness to an event that challenges our understanding of stellar death. Perhaps we have observed the first Superkilonova. On August 18, 2025, the LIGO and Virgo gravitational wave observatories recorded a disturbance in space-time. The signal originated from a point 1.3 billion light-years distant, a distance so vast that when these waves began their journey, multicellular life on Earth was still in its infancy. The characteristics of the gravitational wave suggested a binary neutron-star merger. Two ultra-dense stellar remnants, each the compressed core of a star that once burned in the cosmos, spiraling together in their final dance. But embedded within the data was an anomaly. At least one of these neutron stars appeared to possess a mass below that of our Sun. This presented a fundamental problem. The physics of stellar collapse imposes a minimum mass on neutron stars, approximately 1.4 solar masses, a threshold related to the Chandrasekhar limit of iron cores. Every neutron star ever observed has exceeded this boundary. Yet here was evidence suggesting otherwise. Within hours, optical telescopes began their search. The Zwicky Transient Facility at Palomar Observatory identified a transient source, a point of light where none had existed before. Coincident in both position and time with the gravitational wave detection. The light was red. It faded rapidly. These characteristics matched the Kilonova observed in 2017, an event where the collision of neutron stars forged heavy elements through rapid neutron capture. Gold, platinum, elements born in violence, scattered into space. 11 observatories across the globe joined the observation campaign. Each wavelength, each spectrum, another piece of data in an emerging puzzle. Then the light curve diverged from expectation. Instead of continuing its decline, the brightness increased. The object was brightening again. Spectroscopic analysis revealed the presence of hydrogen, an element characteristic of supernova explosions, not neutron-star mergers. The observations suggested something unprecedented, features of both a kilonova and a supernova occurring in the same event. The concept of a superkilonova emerges from theoretical astrophysics. Consider a massive star in its final moments, rotating with extreme velocity. When its core collapses, the angular momentum prevents direct accretion onto the nascent compact object. Instead, material forms a disk, a rotating structure of plasma and exotic matter. This accretion disk exists in an environment of extraordinary density and temperature. Electron capture on protons shifts the composition toward neutron-rich matter. In such an environment, the Chandrasekhar mass limit decreases, allowing stable compact objects to exist at masses below 1 solar mass. Gravitational instabilities may cause the disk to fragment. The process resembles, in principle, the formation of planets from protoplanetary disks or stellar formation in the accretion disks of active galactic nuclei. But here, the outcome is different. The fragments collapse into neutron stars, subsolar neutron stars that should not exist according to conventional stellar evolution. These objects do not remain isolated. Orbital dynamics and gas drag draw them together. Within hours, perhaps within minutes of their formation, they merge. The result? A kilonova, the signature of heavy element synthesis embedded within the expanding envelope of the supernova that gave it birth. 2 explosions, 1 event. A superkilonova. Now let's be honest. Scientists aren't 100% sure this is what happened. The gravitational wave signal was weak. There's maybe a 1 in 2 chance it could have been just noise. And there's a small but real chance that the exploding star and the gravitational waves aren't even related, just a cosmic coincidence. The light fits some supernova models pretty well, but there are these weird quirks in the colors and the spectral features that don't quite match anything we've seen before. Plus, if there was really a powerful jet from the merger, we should have seen radio waves and X-rays. We didn't. So yeah, mystery still unsolved. But here's what gets me excited about the future. Better gravitational wave detectors are coming online in the next few years. More sensitive, better at pinpointing exactly where these events happen. The James Webb Space Telescope could take infrared spectra of the next one we find, directly revealing what elements are being created in these explosions. New survey telescopes are about to come online that will catch these events earlier and watch them in more detail than ever before. And if this superkilonova idea is right, we might start seeing some really weird gravitational wave signals. Like, imagine detecting one neutron star merger and then seconds or minutes later detecting another one from the same explosion, or a neutron star merging with a small black hole that just formed. We're talking about a symphony of signals from a single dying star. Gravitational waves, light, maybe even neutrinos all coming from the same event but different stages of the explosion. The candidate superkilonova observed in August 2025 may prove to be the first of a new class of astronomical phenomena. Or it may prove to be a chance alignment, an unrelated supernova occurring coincidentally near a marginal gravitational wave detection. Both outcomes advance knowledge. Confirmation would reveal new physics. Exclusion would constrain models and sharpen our understanding of probability and coincidence in multimessenger astronomy. The universe continues its experiments, indifferent to our categories and expectations. We observe, we measure, we construct models and test them against reality. And occasionally the data suggests something we had not imagined. In time, more sensitive instruments and accumulated observations will resolve the question. Until then, we watch the distant cosmos, waiting for the next signal, the next photon, the next whisper from the deep.